So today, we get to talk about something called the Law of Sines. It's just simple proportions. So this applies now to oblique triangles. Oblique triangles. Oblique just means leaning. So this is dumb. If I were to draw a right triangle, we would say that's erect or straight up, right? Oblique just means that it's tipped over in some fashion or tipped over inward in some fashion. So, in other words, no right angles. That's what oblique means. So, in order for us to solve oblique triangles, you need to know the measure of at least, and here's the key, one side and two other parts. So, how does that look? We either have one side and two other sides. We have one side and an angle side. We have one side and the angle surrounding it. Or we have one side and a side angle. By the way, step 4 is going to, there's going to be some situations where this method, side-side angle, and if you turn it around, it's angle side-side, is going to be what's called ambiguous. There's some unclear options for this one. The first 3, side, 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 side angle, side, and angle, side, angle, will always work. So, let's look at the law of sines. Now, number 1, we have to identify vertices first and corresponding sides. It never matters the pattern that you do this, but one vertex is called capital A, so the opposite side is lowercase a. Another vertex is capital B, and the opposite is lowercase b. And finally, the same thing applies for vertex capital C, lowercase c. It never matters which is which, just as long as you're consistent. Be consistent with the opposites. Be consistent with the opposites. All right. Now there are 2 types of triangles. One of them is an acute triangle. That is, every single side is acute. Or excuse me, angle is acute. That actually looks not acute, but we'll pretend it is for now. So all 3 sides are acute. And our other option over here would be an obtuse, where one of the angles are obtuse. Again, it never matters if you call A obtuse or B obtuse or C. The key is be consistent. A corresponds to A, B corresponds to B, C corresponds to C, or is opposite of each. Alrighty then. So instead of talking about sine of A equals the opposite over hypotenuse, since we don't have a hypotenuse, this is the rule of sines, and it's so uncomplicated. Your side length A is over the sine of A, the angle, equals the side length B over the sine of B, equals the side length C over the sine of angle C, or vertex C. And that's it. From there, we just solve proportions. This is an extended proportion, and we solve them. So example number 1. We have to solve the triangle, and we're given one vertex, 24.3, another vertex, 54.6, and we're given one side length, 18.1 inches or feet or whatever. First thing to consider is, if we know 2 angles in a triangle, how do we find the third angle? So, remember that to find out what B is, all we have to do is add these 2 together and subtract from 180. The triangle sum theorem says that the sum of 3 angles of any triangle will be 180 degrees. So the measure of angle B is equal to 101.1 FM. Do you ever know? Okay, now we're able to set up our proportion. So A, we don't know what side length A is, but we do know the angle A, 24.3 degrees. For the B, we don't know length B, but we do know the angle at the vertex B, which is opposite. We know the value of side length C, it's 18.1, so that goes in the numerator, and we know the value of angle C, which is 54.6. So what do we do now? Well, the key thing is here's one proportion. So I can cross multiply or some other method, whichever it takes. So I can do this. But remember, here's the super shortcut with proportions. Multiply diagonally, divide down. Multiply diagonally and divide vertically. So to get B by itself, it's pretty much just two things. Multiply these and divide by this one down here. So I don't actually have to cross multiply. So let's see what that looks like when I do it. I get B is equal to the product sine of 101.1 times 18.1, all divided by the vertical. Multiply diagonal, divide vertical. And so I'm going to put sine of 54.6 downstairs. So now we're going to plug this into our calculator, and we'll get an approximate value. B is approximately, and we remember to change our setting in our calculator to degrees, and we get approximately 21.8. And whatever my units are, this one doesn't have them. So how do we set up the other one? So when we set this one up, I can effectively ignore this guy entirely right here, and do my proportion using the first and the last and the first and the last here. So when I set up for A, it's going to look like this. A is equal to the sine of 24.3 times 18.1, all divided by the sine of 54.6. And notice this is exactly the same as the previous entry, except I changed my angle there. 18.1, 18.1, 54.6, 54.6. Now all we have to do is plug that into our calculator. Get approximately 9.1. And now we've solved this triangle because we know the value of all 6 parts. So let's now look at the next situation. We have a pole that tilts toward the sun at an 8-degree angle from the vertical, and it casts a 22-foot shadow. The angle of elevation from the tip of the shadow to the top of the pole is 43 degrees. How tall is the pole? So let's draw a little pole that's leaning slightly, 8 degrees. A little grass growing out from the pole. It's leaning towards the sun, so I'm having the sun over this direction. I have a shadow that's on the ground, 22 feet. Bloop, bloop. Bloop, bloop. The sun's rays go this way, which are not physically shown, but I will draw them. And we are looking for the height. And notice the height is not a vertical. It's not 90 degrees. Now, what did it say about its degree? How much off the vertical is it? It's 8 degrees off. So 90 degrees would be straight up. So it's just 90 plus a little bit more, 8. So that means this one's 98 degrees right here. We are told that the angle of elevation is 43 from here up. The triangle sum theorem tells us now that I can find this one just by subtracting those two from 180. Get 39 there.
Why do we know 98 degrees?
So as long as we're consistent, we can now set things up. Notice that this 43 has to correspond in the fraction with the h. So I'll put h in the numerator and sine of 43 in the denominator. Now, I do not need the 98. Why? Because it corresponds to this red long side, and I don't need to find that. I'm only asked to find out what h is. So I'm given the 22, which has to be fractionized with the 39. So 22 is the length, so I'm putting it in the numerator, all over the sine of 39 degrees. So now we can start cross-multiplying and dividing. So again, multiply diagonally, divide vertically. So we get this, and plug that into your handy-dandy calculator. And what? 23.8 loquito feet, which of course makes sense if my diagram is to scale. I expect this shadow to be roughly near that one.